So we will be starting with the first topic of the day, and this is case of success at INM Colombia, application using R as a programming language. The presentation will be in charge of Daniel Melo of INM from Colombia. Daniel has a degree in physics and is currently studying a master's degree in physics at the National University of Colombia. He works in the liquid volume laboratory of the Meteorology National Institute of Colombia. He is involved in different projects at INM as maintenance and expansion of the laboratory's R software project for the creation of R programming community at INM Colombia and project for the development of a national standard for a liquid flow. Welcome, Daniel. Please go ahead with your presentation.
Thank you very much, Diego. Good morning to everyone. I am Daniel Melo. I work at the Liquid Volume Laboratory. And today, I would like to show you a program that we built using R language as a tool for quality assurance of our measurement processes. First of all, let me tell you a little bit about this project's motive. So, we as a laboratory, we have access to large amounts of data every day. We have calibration services data that is related to CMCs. We have our own equipment's calibration records that are useful for quality assurance. We have laboratory comparisons, both national and international, and so on. But we specifically, we felt like we were not taking full advantage of all this data that we had access to. And it was not because of lack of resources. For example, we have an institutional platform to store calibration records of our equipment, and it works. But we were not fully satisfied. And we realized that it was because each laboratory has its own very specific set of needs regarding data processing in order for this data to become relevant information for the laboratory's personnel and ultimately for this information to become knowledge that supports decision making in the lab. Of course, there are some broad requirements that are shared among different laboratories. For example, mass standards and glassware both have maximum permissible errors. But on the other hand, we as a volume laboratory, we have maximum permissible uncertainties for our weighting instruments that are used in the calibration of glassware. So the specific requirement might be just as important as the general requirements. And so going back to the main topic, we identified these two key facts: large amounts of data and specific set of needs. And from these two, we concluded that we needed to build our own program for data processing, because we were the ones that really knew and understood what we needed and how we needed it. And so it was born this program. So we began our program. And when we are dealing with data, the easy choice is to use the R language. This language, its perks regarding data processing and statistical analysis and computations are well known. But actually, there was another main reason that led us to choose the R language, and this reason was the Shiny library. Shiny is an R library that is focused on interface building, and it gave us the advantage to focus more on the statistical and technical sections of the software, and not so much on the interface building, which is usually a very time-consuming stage of software development, especially for not so experienced developers like we were, and like we are actually. So time proved this to be the right choice for us. But anyway, I will let you judge for yourselves. So now I will actually show you how the program is and how all these that I have said finally worked out for us. So give me a second, please. Here we have the R code. We run our app. And well, here it is. This is kind of the front page of the program. To the left, we have some sections with essentially some general information about the program and about our laboratory. For example, here we have the version history of the software. It has had 4 versions. The first one here in May 2020 was kind of a first draft. Essentially, it was just like the front page, nothing else. Now in September 2020, we had the first actually working version of the program. It was built by a former member of this lab, a physicist called Cristian Gonzalez. And this version remains to be the core of the program. These last 2 versions in 2021 have essentially some new functions that were implemented by me, but the main core is the version 1.0. Well, this next section here is actually pretty interesting. It is one of the new functions that was added. Let me give you a bit of context. Here at INM, each laboratory is required to submit monthly some kind of calibration calendar for its own equipment, in order to check if they are up to date, or maybe someone is lagging behind, and so on. This task was of course performed manually in a specific form that we have. But we realized that in this program we had all the information necessary to actually complete the form. So we thought that it might be a good first step towards a deeper process automation to try to make this form completion automatic. And the result of that idea is what you are seeing right now. Here we can tell the program on which date we want our calendar to be built on. For example, if I choose, let's say, 18th March 2021, the program will give me a calendar as it was written on this date. Then we have here two options, two further options. The first one allow us to tell the program which kind of instrument we want to include in our calendar. For example, here we can include only standard instruments that are labeled as standards, and here we choose only instruments that are labeled as currently in service, or both. We can actually choose both. But well, for the sake of the example, let's stick to the general case. So here I click here and I get I actually build my calendar, and I can download it here. As you can see, well, I'm not sure if you can see, but the name of the file is updated with the prescription that I gave the program to build the calendar. In this case, it was only the date. So let's download it here. I had another one, but it doesn't matter. It's the same. Now we can open the file. Some format problem here with the data. It's just a minor issue. So this is what we get from the automatic completion of the form made by our program based on all the data that we have in our lab. In this first column, for example, we can see if the calibration is performed outside our lab or in a different lab or inside our own lab. For example, these are mass standards, so of course they are performed outside our lab. And here we have a tank that is calibrated here in our own lab. In this column we have some general information about our instrument. Well, this is an internal serial number here at INM. But the most important information here are these 3 dates. We have the last calibration, we have when the next calibration should be, and when it has actually been performed. Or if it is blank, it means that it hasn't been performed yet or recently. For example, we see here that this tank is kind of lagging behind the date because, well, this is actually an instrument that is currently out of service. So you can see why it was useful, the option that we included to choose only in-service instrument or standards and so on. And well, this is kind of everything this automated process does. So let's go on to the next functions. Well, these other sections of the software are not that interesting for you. Are just like documents and user manuals. So I won't bother you with that. I will go to this section. This section is the main core of what this software is now, and its essential purpose is to provide us with every single bit of information that we might need from our instruments. So here, as you can see, we can this section is classified between different kind of instruments. So for the sake of the example, let's choose this weighting instrument, and let's choose this particular balance. We have an XPR1203S Mettler Toledo. We have here 4 sections. We are in the first one. This one has like some general information, some kind of data sheet, and some information about how we use this instrument, which intervals, for example, we use this instrument in our volume calibrations. But this section is not that interesting. We have now a photo, nothing interesting either. And then in this section, things start to get a little bit better. This section contains every bit of numerical data related to calibration records of our instrument. For example, here in this first table, we have some kind of summary about the 3 calibrations that have been performed on this weighting instrument. We have here date of calibration, time that has passed between calibrations, certificate number, and so on. And here we have the 3 kind of tests that are performed on each calibration: eccentricity, repeatability, and measurement error. Now here in this next subsection, we have some more specific information about calibration records. We can choose if we want data related to eccentricity, repeatability, or measurement error. Usually we use this section when we are completing a spreadsheet and we need information about measurement error on some specific point. So let's say, for example, 400 grams. So here we have it. We have the measurement error results on 400 grams with its uncertainty, expanded uncertainty, coverage factor, and so on. This is useful also, for example, if we want to make an estimate of the historic deviation component for our balance. We can compare here quickly and easily results from different calibration certificates. Otherwise, we would have to access one calibration certificate, then the other one, then this is much easier than that, much quicker also than that. We can check, for example, only repeatability results. We have them here. For example, this point. Here I can check if my balance perhaps is performing poorly or more poorer. I can check if my balance performance is poorer with time or not. So I can see if maybe it is requiring maintenance or it is just fine. Maybe it's very, very useful. But of course, if I want to make a deeper analysis or a more general analysis about the calibration records of my instrument, well, maybe a table full of thousands of numbers is not that useful because we are just not that smart. We need some help, and that help is provided here in this last section, and where we can find all the data that we had here in this section, but summarized and classified in the form of figures. Here we have the 3 calibration tests that are performed, and this last section is for the specific maximum permissible errors, in this case maximum permissible uncertainties, that we as a volume calibration laboratory require. So well, let's see this first section about eccentricity tests. We can choose which interval of dates we want to focus on. For example, perhaps I just want the last two calibration certificates, so I just restrain the figure to this interval. Each color here, each line represents the results for one specific point. You know that eccentricity tests are performed on different points in the weighting plate of the balance. So I can here choose which points maybe I want to focus on, maybe everyone. I can change here the units in which I want the figure to be displayed. I can choose here if I want absolute eccentricity results or maybe relative ones, and well, so on. The repeatability section it is actually quite similar. Quite similar to the eccentricity one. As you can see here, it is easier to actually see changes in the performance of the balance now that we have it in a figure. It's much easier for us as humans, rather than in the previous section when we had just a table. And well, in this we can also here see one specific calibration certificate and how the results change over the different points that were used. And finally, one of the most interesting sections of our program, we have the calibration, the actual measurement error results over time. So here we have this graphic that is focused on the 1 gram point over time. We see here the 3 dates in which there were calibrations, and we see that the point is actually performing quite well. It is quite stable over time at this point, up to this date at least. Again, we have here these error bars that are actually standard uncertainty. We can change them here for expanded uncertainty. We can change here the point which we want to display. And in an analog with the repeatability test, we have here the results for one specific calibration certificate and how the results change over points. Well, again, here you see the points, the measurement errors, the error bars, and these tiny x's that you see here are a new function. Those are results of intermediate checks, and well, it let us really enhance the utility of intermediate checks by letting us more easily analyze the relation between intermediate checks and its corresponding calibration results. It's quite interesting, that one, quite useful, especially. And last one, we have here our measurement error, maximum permissible error, sorry. We can choose which point we want to check on. We are comparing here with the limits proposed by ISO 4787 from 2010, which is the glassware calibration standard. We see here that for the 1.2 kilogram point, our balance is performing just fine, and it is well, it is good ready for use in this point. And what we can check other points also. It is quite nice, and it reduces the probability that we use an instrument that is out of requirements for the use that we want to give it. Well, here we have the same for a specific calibration certificate, as I told you with the previous sections. And well, I'm not sure in what time I am, but well, we have some like future developments that are currently that we are currently working on, like some. Well, I will tell you especially about the spreadsheet. Our current focus is to develop a spreadsheet that kind of completes itself up to some point with the data that we have here. For example, the measurement error data, the eccentricity test data that we usually have to write in a calibration spreadsheet. Well, it can be written by itself, and it makes life much easier for us, the laboratory members. Well, I think that's kind of enough. That's what I wanted to show you today. Thank you very much for your attention, and we may go on to the questions section if you like.
Thank you, Daniel. Thank you for your participation. So I think we have very many questions. So let's go for that question. So I have the first one from Francisco Flamenco. Have you tried to use the same program or the technology behind this program in other metrology laboratories?
Yes. Actually, because of the success that this program showed in the volume laboratory, we, with the help of a quality management group member at INM, Linda Petro, we made a project to make some kind of knowledge transfer to every laboratory here at the INM, which is interested in developing some kind of program similar to ours, in order to make their learning curve well better, to help them, and so they don't have to make this path alone, like we had to. Yes, we are doing.
Okay, so I have to filter some questions, sorry, but all the questions they are going to be stored, and Daniel can ask them later. Yes, because we don't have time to answer all the questions. Sorry. So the second question I want you to answer is, how much time did you invest in developing this tool?
This tool, as I said, was developed by a former member of this lab, and he developed it during the time in which the laboratories were closed because of the pandemic, so around July and June. So I understand that it took him about 2 months to build the main core of what the software is today.
Okay. Another question is, are you applying predictive evaluations, or is it possible to make predictions?
Well, I'm not exactly sure what you mean about predictions, but maybe this is related to that. We are working also in some kind of algorithm to make an estimate of the calibration interval of our instruments. And the idea is that this algorithm, of course, is based on the historic deviation that each instrument shows. So in some point, it is kind of predicting how much time we can be sure that our instrument will not be out of statistical control.
Okay. Another question is, does the software has a reminder, like an email for the technician to know when he has to calibrate its own standard? Or it's I think he refers to a time slot that it focuses a time slot in your calendar. Yes.
Like if it were like connected to our Gmail account to
Yeah.
like,
yeah.
I haven't thought of that. No, it has not that function, but it might be pretty nice actually.
In Inti we have that for that application that sends a mail when the calibration must be performed. So that's, I think that's why he asked that question. A question is, thank you, Daniel. Thank you very much for your showing us this analytical approach for digitalization. I think that someone asked the name of the software of this application.
It is called here it is, LaBif.
LaBif. Okay. A question on Jose Osegueda. What are the advantages of using this software against Python?
Against Python?
Yeah.
Well, one of the main advantages that I have realized by using this software is that the R language is, I think that it is better suited to work with data frames than other languages, also including Python, I think. So I think that would be the main advantage. The handling of data frames in R is quite intuitive, and it makes it quite easy to perform statistical analysis on the data frames that we are using.
Okay. Another question is, how do you get information for each measurement? I think it's how automatically takes the information from the standards.
Well, this maybe you mean about because of what I talked about the spreadsheet that we were working on?
Maybe, yes.
Well, the automation that we were planning for the spreadsheet, where it wasn't focused on the measurement acquirement, or the data acquirement, but rather on the metrological features that we have to give the spreadsheet in order for it to estimate uncertainty, to correct the indications of the instrument. So it wasn't really aiming to that kind of function, although it might be useful, but I think it may be a bit more complex than what we are thinking.
Okay. I have another question from Vanessa Cardenas. I wonder if all the data you feed to the system remains in the cloud and other members of the group have access to it. is this sense. Could you please share the significant advantages the group have had using this approach in terms of data accessibility?
Sure. Well, right now, this software is based on a shared folder, an internal shared folder of the liquid volume laboratory, to which every member of the lab has access. And also, well, in this shared folder, there is the database that is essentially like hundreds of the spreadsheets, and also the actual code of the software. The advantages about data accessibility. Well, I mentioned some when I was going through the calibration records section. For example, if you want to compare calibration results from different certificates, usually you would need to open one certificate, open the other one, see one and the other one, But with this software, you can see them both here, and if you want to change from one instrument to another, you can make it with just 2 clicks. Otherwise, you will have to open another certificate, the other certificate, and it is tedious and it is error prone for the lab member.
Okay, I think we have the last question from Jose Segueda. How much lines of code this app represents, and how do you maintain this app updated? I think it's a hard question. Yes.
The lines of code, honestly, I'm not sure, but many thousands. I mean, probably tens of thousands. And to keep it updated is mostly to keep updated the database, because well, of course we cannot check on the actual code very frequently, because it's just very sad to do it. We do it like from some time to time when we want to make a new function, to implement a new function. We check the code in order to make some kind of validation that is useful also.
Okay.
To correct errors and so on.
Excellent. Well, thank you, Daniel Melo Porras, for your presentation.